Ben, you'll keep time again? Great, thanks. So, didn't get as far as I wanted last time. We'll talk about breaking the loop. Hopefully we'll spend some time talking about gain enhancement with positive feedback structures as well. If we take this amplifier structure and include modeling of the input impedance and the output impedance of the A amplifier, and include the load resistance, we can sum currents at 3 nodes in that circuit, and write these 3 equations. And it's not too hard to solve. And we find the gain with feedback is given by this expression here. And of course, my goal is to find the loop gain. So if we don't have the loop gain, we're going to have a hard time doing things like gain and phase margin determinations. What's the loop gain when you look at that expression? Can you see what the whole thing's here, right? I've included everything. I haven't made any assumptions. What's the loop gain?
You'll have to divide out one of your terms in this denominator to get it.
Yeah, I want it to be 1 plus something, right? 1 plus A times something. So here's the A times something. So if I divide through by this big long term here, I'll have 1 plus A times something. I'll be in the standard form that the denominator needs to be to read off the loop gain. So if we divide through by that big long term here, we finally find that the loop gain is the product of AB and this term here that involves a whole bunch of, it involves input impedance and output impedance and the resistors in the beta network and so forth. So here's the loop gain. Now, I can multiply through by what we think of as 1 over beta, as beta, excuse me. So I multiply and divide by beta, and I can rewrite the gain like this, where this is now beta, and this is what we might think of as overloop gain, AVL. And if you're going to do Bode plots or Nyquist plots, and you want to look at where the voltage gain intersects the 1 over beta curve, you need to express it in this form. So this is the gain expression we're going to need to work with. And we see that the gain expression is strongly a function of AV, of RN, of ROut, of RL, and of the components that are used to make the beta network. So we see that the AVL, the loop gain, is affected by both its own input and output impedance and that of the beta network. And this is a real messy expression. And in fact, when we do calculations with loop gain, we normally, if we're going to use phase margin criteria, we like to assume that A network is independent of the beta network. And then we put the 1 over beta line in for different values of beta. Now what do we find here? Not only do you have to know what beta is, you have to know how you realize the beta network to correctly get the AV, if you want to put the 1 over beta line in. Okay, so probably any analysis that doesn't result in this expression for AVL is going to introduce some errors in the calculation of phase margin. Make sense? Any break in the loop that does not result in this expression will result in some errors. They might be reasonably small, but there's going to be some errors. So most authors talk about breaking the loop, They give an algorithm for breaking the loop, and then they ignore the fact that the loop gain that they calculate may not be the right loop gain. In many, if not most applications, breaking the loop will alter the loading of either the A amplifier or the beta amplifier or both. So what we like to do is break the loop in such a way that the loading effects can be approximately included. We probably won't get this expression perfectly, but at least get a good approximation. Also, we can't screw up the Q point when we break the loop. If we screw up the Q point, some transistors may go into a different region of operation. So consequently, most structures, a broken loop only gives an approximation of the actual loop gain. Some structures, not even real easy to break the loop in a way that seems to make sense. So here's one standard way to get the loop gain. We break the loop if it's a voltage series feedback structure. We break the loop as we'd shown before. We terminate both sides with their ideal input and output impedances. And what that does is it neglects the loading of the A network on the beta network, but it includes the loading of the beta network on the A network. But this voltage across here, if I break it this way, this current through here is 0. Actually, there's some current flowing through here, and that current that will be flowing through will be the quiescent current. So what we want to do is terminate this side here. This is good for small signal analysis, but not for large signal operation. So we would like to put a DC current source in here equal to the quiescent current that would have been flowing there. And this is an AC short circuit. This loop gain analysis is based on AC analysis, not DC analysis. So we would like to replace this by a DC voltage source equal to the quiescent voltage that was across the output of the beta network. And now we should have the open loop amplifier biased correctly as well. So we've broken the loop and we biased it, and we can get a fairly easy approximation for a loop gain by doing this. So if we apply that strategy, the loop gain by the terminated loop looks like this. We can calculate it for the structure. And here is the actual loop gain. And we see that there's a little bit of difference. There's a GN that's missing right here, and there's a GN that's missing right here in our loop gain expression. Yes, Jake?
Sorry.
This is a better way to break the loop. So what I'm going to do is put 2 beta networks in. I'm going to break the loop here and here. And so when I look back in here, I'm going to terminate the input to the beta network with what I say the output of the A amplifier. So I take the beta network and terminate with a short circuit on this side. And then I'm going to terminate the beta network for the purpose of loading by the ideal input impedance, the A amplifier. So I put an open circuit right here. So this is another way we can get the small signal model for the loop gain. And this will be a little bit closer to what's going on. Of course, I still need to terminate these with, if I want to do an analysis in Inspector, I need to be sure that we don't mess around with the Q point. So I will terminate this short circuit here for DC analysis with the quiescent voltage across here in the original circuit, right here. And I will terminate this open circuit that I want with the quiescent current that would have been flowing there. We have a whole bunch of different feedback structures. So I'm going to show the terminations that we would have for breaking the loops with the different types of structures. So the one here is the voltage series feedback. You can sample the voltage and carry it back in series with the input. And here's the termination that we have. This is a current series feedback. So we sample the current, fit it back in series with the voltage. So again, we take the same strategy, put two beta networks in. Beta network 1, beta network 2. Since we're sampling a current, the output impedance here should have been infinite. So we terminate the right side of this beta network with an open circuit. And since we're feeding back something that's in series with the voltage, we expect the input impedance of that circuit to be infinite, so we terminate with an open circuit here as well. So this is how we would terminate the voltage series feedback scheme. There's 4 different basic feedback structures: a voltage shunt feedback scheme, and a current shunt feedback scheme. And here's the terminations on those corresponding beta networks. Make sense? Okay, so we've got a way to get a reasonably good approximation for the loop gain, although it still has some errors. So let me look at open loop gain simulations for a voltage series feedback scheme where the A amplifier and the beta amplifier are both voltage amplifiers. This is a common simulation circuit we set up. We first of all put the common mode input voltage that we want for our amplifier, find out where we're going to operate it at. Put a small signal input in and put VXX in to trim out any offset voltage that we may have on the amplifier. And then we terminate the output of the amplifier with the load. And the load would include the beta network. Include any loading, including the loading of the beta network. So if there's a resistor on the output and there's a resistor divider, then this load would be RL in parallel with a series combination of those two resistors. Okay. And that termination network needs to be biased correctly so it doesn't change the Q point of your amplifier. If you do this for simulation, this gives us a loop gain. If you change anything in your circuit, you probably have to change your loading again. You have to change VXX again probably as well. This is a way that is probably easier to work with. So with a previous structure, it's a little bit of a hassle to anytime you change something in the network to go in and retweak out the offset voltage with VXX and retweak the termination bias on the load network. So here we're going to try to calculate the open loop gain of the amplifier in a feedback configuration. What I have here is the load termination like I had before. And now I'm going to provide feedback. And it's called a test beta feedback network. And I don't want this test network to load down the amplifier at all. So I'll put an ideal voltage buffer on the output. And this goes to a test beta network. And I don't want the A amplifier to affect the beta network. So I'll put an ideal buffer on the output of that as well. So now I have a feedback network. And this stabilizes the effect of the systematic offset voltage when you're in feedback. The test beta network that I've got here may not be related to the actual beta network at all. The actual beta network might have a beta of 1/2. The test beta network might have a gain of 0.01. Okay. Loading of the actual beta network is included with load termination. So the actual beta network we're going to put on is included here, at least the loading. The voltage gain now is what we want. We want the gain of A amplifier. We assume we know what the beta network's probably an attenuator. So to get the gain of the AV amplifier, what we do is in a simulation, we look at V out, and we divide it by V plus minus V minus. V out divided by V plus minus V minus gives us the open loop gain. How about the test beta network? What do we want to do with that? If you do feedback, what causes the most stringent compensation requirements? Large beta or small beta? What? Large beta. If beta is equal to 0, it's open loop. There are no problems with compensation. Beta equals 1 is the most stringent feedback in this situation. It may well be the case that when you start to design an amplifier and you're ready to do some simulations, and maybe your goal is to work with a beta of 1, if you put a beta equal 1 in, it may oscillate even. You may be a long ways away from being correctly compensated. If you try to simulate that open loop amplifier in a feedback configuration and it oscillates, it's not very good. So what you might do is you might say, let's put a test beta of 0.01 in there. 0.01 might be a small enough beta that the feedback amplifier will still be stable, even if you don't have anywhere near the right compensation for beta equal 1. You may not need any compensation for a real small value of beta. Does that make sense? So why not just use the actual beta network for the test beta network? What did we say the reason was?
Maybe you're not compensated for the beta.
Might not be compensated for the actual beta that you're after. So you typically want to use a small beta in your beta test network. Oh, here's another question. Why not just simulate the frequency response of the actual feedback amplifier? And look at the magnitude of the gain to see if that's what we want. Forget about this monkey business with the pole locations. Forget about this monkey business with the phase margin. Just look at the gain of the amplifier. We can do that easily now, right? We can do it in 1950 easily. We can do it easily now. Will that work?
That wouldn't tell us anything about the loop gain, though, would it?
Who cares about the loop gain?
I thought we did.
Well, why do we care about the loop gain?
Well, I thought that it told us everything we needed to know about our practical parameters.
No, it didn't.
Isn't it?
The loop gain gave us an indirect way to try to compensate an amplifier, so hopefully we put it in an application that's good. So let's just put it in the feedback amplifier we want to work with and look at the magnitude of the gain. If the magnitude of the gain is what we want, we're good.
Is it because our beta is not constant?
What?
Is it because our beta is not constant?
Put the beta you want in. If you want a beta of one third, put a beta equal 1/3 in. Use the actual resistors you're going to use in your beta network. Can't get any better than that. Right? Pardon?
What if we change our betas? I don't know. Later on, I'm wrong.
If you're using the catalog part, you put beta equal 1 in. Right? That's your worst case situation. What's wrong with this? Or is it a good solution? Maybe it is. Tim, you seem to have a questioning look on your face.
It seems kind of more like a guess and check approach. Doesn't it, to simulate?
Good observation. It might be a guess and check approach. So that's a good concern. But you get a little bit of problem with phase margin also. You simulate phase margin, You say, well, it's 45 degrees. I want it 65 degrees. We don't have a closed form expression that relates any of the design variables to that phase margin. The phase margin is real nasty to calculate analytically. So you kind of still have the same problem there. It's a good concern, but still have the same problem there. And furthermore, probably all you're going to be doing maybe at this point is changing that compensation capacitor. So you just go in and say, I'm going to change the compensation capacitor now and try to bring that magnitude response into what I want it to be. A lot of times you do that with the phase margin. Phase margin is not right. Too high or too low. Increase or decrease the compensation capacitor a little bit to bring it in. If the amplifier is overly underdamped or oscillatory, won't that show up? If the real circuit is oscillatory, it's going to oscillate, right? Will our simulator show that? Why won't it show it?
We're not playing the right
Can't
trick.
see in the voting plot, right?
You know, why can't you see it in the Bodie plot?
Because you're not.
You just look at the magnitude.
Yeah.
You can see it in the step response.
Okay, so we might look at the step response in the time domain. Good observation. Might look at the step response in the time domain, and then you would see it. But keep in mind that when you do a Bodie plot, it linearizes the network at an operating point, and it just looks like looks at a magnitude of the transfer function, right? Magnitude of the output for a given input. So it won't show up in the magnitude response, although it would show up if we put a step in. Another reason that we can't look at the magnitude response, a lot of times if you have a problem with an amplifier with bringing in the step response, you also have overshoot the magnitude response. But if you look at the magnitude response is identical for symmetric zeros and poles in the transfer function. If you have a pole here and here, or you have a pole here and here, and the magnitude response will look the same. Make sense? So you can't see stability issues in the magnitude response. Now, if the poles were here, you might see overshoot in a magnitude response. Of course, you couldn't tell the difference between that and this, but in either case, it would be unacceptable, right? But in some cases, you could get fooled.
Why don't we try?
Yes?
Why don't we try plotting the open loop gain versus 1 over beta?
How do you get the open loop gain?
Well, if we're in simulation, can't we use unrealistically large capacitors and inductors in our schematic so that when Cadence is trying to calculate DC versus
Okay, good idea. We can get the open loop DC gain. Open loop DC gain doesn't tell us much at all about stability, or it doesn't tell us much at all about time domain performance. So if you put ridiculously big components in, you might get fantastically good. You just put a ridiculously big compensation capacitor in, and everything would appear to perform well. If it's sluggishly slow, it would appear to perform well when the real system won't. So let me briefly mention tools that help give you insight in regard to compensation. Compensation is not trivial. Conceptually, it looks like it's pretty straightforward. When we start to have to worry about breaking the loop and looking at the loading effects on the loop, it becomes more challenging than it might appear on the surface. So a lot of times we use tools to help us out. MATLAB is great for giving us insight into how the system performs. If you've got analytical models for what's going on. There are several toolboxes that are set up primarily for control systems that are great for characterizing feedback amplifiers. Cadence also has some tools that are specifically set up for doing this. I kind of almost talked about one thing we could build on our own, and that is embed the amplifier in a feedback network. Well, they do the same thing, and they call that the STB analysis. And so you can run STB analysis in Spectre. Has anybody worked at STB analysis? Where have you worked with STB analysis?
Oh, we've been using it to look at
In
our
our
labs.
In the labs? Oh, great. Super. Thanks, Ben. You can see I had a lot to do with it. Let's change directions. So we're done with talking about compensation. I'd like to look at other ways to enhance the gain of an amplifier. You'll recall when I looked at the different strategies for building amplifiers, that we're going to take a break now. We're going to go build two-stage amplifiers, and we're going to come back and look at other ways to increase the gain. So let's talk about that now. We looked at ways of increasing the output impedance of the amplifier. We had the cascodes, the regulated cascodes, the folded cascodes, and so forth. We looked at ways to increase the transconductance. That was in that numerator. And the only thing we looked at was what the current mirror, putting the current mirror on. And we didn't really gain much there. We thought it was a good idea, but in the end, it didn't really help us much. The reason it didn't help us was the output conductance increased proportionally. So we had no net improvements. We looked at cascading. We spent time looking at the two-stage structures. But we have the compensation issue. It's easier to start with a high, if we can start with a higher gain or higher gain bandwidth product, even to go to two-stage, it makes our designs easier. So go back to our original strategy and see if there's a way that we might be able to increase the numerator. So one way to increase the numerator is to drive both the quarter circuit and the counterpart circuit. So what we've been doing so far is we just putting a bias source on this counterpart circuit, put a biasing current source in. We've thrown away one of our inputs. If I tie these together, what's going to happen? Am I going to get destructive interference, and what I gained with this one's going to be lost with this one, or it's going to be constructive, and they both contribute to the gain? Make sense? What's going to happen if I drive this that way? What? Destructive. George, do you agree?
No.
Okay. It's going to be constructive. Why is it going to be constructive?
Would it increase your GM?
It's going to increase the GM. Remember, the small signal gain expressions were identical from the quarter circuit and the counterpart circuit. So the outputs are going to add together. So it'll be constructive, not destructive. So the gain is going to be inverting GM of the quarter circuit plus GM of the counterpart circuit over the sum of the two gains, and the transconductance gains will both be the same sign. So this is real. This is not like the current mirror, it's going to go down. We'll show that this is real. So here's this way to do it. What?
It's an inverter.
That's an inverter.
It's the push pull. It's push pull from lab.
Yeah. And if we want to, we can put tail bias currents on. Tail bias currents on both the quarter circuit and the counterpart circuit. And probably have to put a common feedback circuit in. to establish one of the two voltages, so you can fix one and drive the other and vice versa. Okay, so it's not too hard to do. I think that this method doesn't get as much attention as it really needs. People have certainly been aware of doing this for 40 years. I've seen a few people talking about more recently, again, going back to using it. I don't know why we really have neglected other inputs so much. And here's what the gain expressions look like. If we drive the counterpart circuit in the practical parameter domain, all we've done is added a 1 over Vx's bias 3 term here. And if this is the same as this, we've doubled the gain. And it hasn't cost any power to do it because the current's already flowing through those devices anyway. So we can double the gain. The bandwidth doesn't change. So if we had the same excess biases, we double the gain bandwidth product. Make sense? So both the voltage gain and the gain bandwidth product have improved. And they improved very much. Maybe about doubled. If we make the excess bias of both of them the same, about double. It's not the windfall we got with going to the cascode structures. It's not the windfall in the gain, but recall none of our structures improve the gain bandwidth product. This structure improves the gain bandwidth product too. It's a factor of 2. Cut your power dissipation factor of 2. If you look at a lot of data converters that have op amps in them, a major portion of the power dissipation is in the first stage op amp in those structures. If you can reduce that power by a factor of 2, you will come to close to a factor of 2 reduction in the power required for your data converter. So it's non-trivial. Yes.
For the previous slide, when we talked about like the current mirrors in our previous designs, I don't know, it was like helpful to see how the current was moving through in the small signal and how it summed up to go into the output to double the gain.
Yes.
Can you do that here?
Yes, exactly.
But can you show it just to be sure, like, we know where the current is actually flowing and you hook up the inputs in this way?
Yeah. Now keep in mind, this is now a symmetric network. So these are AC grounds. Okay? So my first transistor, the quarter circuit, and this goes to ground. And my second circuit, the counterpart circuit, and this goes to ground. The drains are connected together. They're connected to capacitive load CL. And the inputs are connected together. And these will be connected to VD over 2. We'll do differential excitation. So if I sum currents at this node, I can say V out times SC, oh, I missed the output conductances. This is G out 1, this is G out 2. SCL plus G out 1 plus G out 2 plus GM2 V2 plus GM1 V1 equals 0. But V1 and V2 are both the same and they're equal to VD over 2. So I can say V out times SCL plus G out 1 plus G out 2 is equal to minus VD over 2 times GM1 plus GM2. Or finally, V out over VD is equal to minus 1/2 times GM1 plus GM2 over SCL plus GL1 plus GL2. Okay. What we had before, this was gone. All we've done is add this term in here. Okay, any other questions? Let's go back to decreasing that denominator. Now we can apply, so I looked at a way of increasing that numerator. Can I do that in a Cascoda structure too? I used a simple quarter circuit. If I used a Cascode quarter circuit, could I also excite both the quarter circuit and the counterpart circuit? Answer is yes. So we can go ahead and get the benefits that we had from cascoding if we wanted. Can I look at a regulated Cascode structure? Answer is yes. Make sense? Folded Cascode? Answer is yes. So let's look at something else now. Ask the question, can I make the denominator smaller? Well, we had done that by cascoding, by regulated Cascodes. That was at the expense of a little bit of loss in signal swing, but it happened. So is it possible to come up with circuits that have a term here that's negative? Is it possible to come up with circuits that will provide a subtraction of conductance in the denominator? Now, the stuff I'm going to talk about for the next 10 minutes or so, these are structures that offer potential. We're not in a situation where I'm recommending this is the way to design amplifiers today, but I want to show that there's some possibility of doing something with it. Okay? So what if I could drive the counterpart circuit with minus V out? What if I could drive the counterpart circuit with minus V out? If I drive the counterpart circuit with minus V out, we can show that the voltage gain looks like this. And what have I done? I've introduced a negative term here. Better be careful what you ask for. So now I got that negative term. Maybe I got more than I wanted. Because what could happen now? How are GMs typically compared to G outs? Much larger. What about this amplifier? If GM is much bigger than the G outs.
You could have the right half plane pole.
Right half plane pole. Oh. Unstable amplifier. Bad idea. Well, it's a bad idea if we want to use the amplifier open loop. We use the amplifier's open loop. No, so it's premature to draw a conclusion. It's a correct conclusion that it's unstable, but it's not a correct conclusion, it's not useful. So we'll address that issue in a bit. So here's the terms of the quarter circuit and counterpart circuit here. What if I put in a signal, instead of putting minus V out, I put in a small fraction of V out?
You decrease GM.
No, this is not driven by V in. This is only driven by minus V out. So what if I put a small fraction of V out in here?
Shrink this size of that negative.
You'd shrink this term here. Maybe I could put a small fraction of V out so that that small fraction of V out resulting in this term and this term being equal in sign. Then what do I have?
Something,
What?
something you could call stable if you wanted to use it that way.
If you want a stable, it's stable. Yeah? How about the DC gain? Could be positive. Let's assume it's exactly the same. Let's assume I put a attenuator on V out, a negative V out, and it's what? Infinity!
We don't like that.
We don't? Why not?
That's not how
Don't be careful before what you throw away. This is pretty neat stuff. So we've got the ability to put that pole, oval pole in right now. Plane that may or may not be good. We got the ability to put the pole exactly on the origin. If you put that pole exactly on the origin, you get an infinite gain. Some people have looked at trying to do something kind of like this. You know, several people make statements, you got to be careful, because if you put that pole, if you make that term just a little bit too big, the pole goes the right half plane. So they say, well, let's take and make that term 2/3 of G out F1 plus G out F2. And then if that gets a little bit bigger, a little bit smaller, we're still stable. Make sense? And so then we might increase the gain a factor of 3. Or maybe we try to make this term 90% of this sum. Then we get a factor of 10 increase. And the argument is maybe we won't have that pole go into the right half plane then. Make sense? So, a lot of gain enhancement capabilities with this approach. How about the gain bandwidth product? Gain bandwidth product was the output connection cancels out. Gain bandwidth product is what we had before. So we get more gain. No, what? We lose bandwidth, but that's not too bad because we don't lose gain bandwidth product. Is bandwidth real important? Is bandwidth important?
It totally depends on the application.
But usually,
Can you find very many applications where bandwidth is important in contrast to gain bandwidth product? So let's look at an op amp. You can go back to any of the op amps you looked at in 230. We also looked at measurement characteristics in the lab in this course. Here's what the gain characteristics typically look like. You have a DC gain A0. You have this pole here, omega 1. And why is it so low in frequency?
because the gain bandwidth product is constant.
Now, that's not the reason. Why is this pole so low in frequency? What did we talk about the last 2 lectures? Why is it so low in frequency?
Because the compensation capacitor has to be small.
You have to have a big pole spread to get acceptable performance. You don't know how to push those high frequency poles any higher. We know how to pull the low frequency pole lower. Okay? So why is it low in frequency? We have to put it down there to be able to get acceptable performance and feedback. And where is this at? This is of the order of magnitude of what?
Tens of
10.
Why not single?
Or even Hertz range, or maybe even lower. If you go to this structure here, it might be in the millihertz range, or the microhertz range. Okay? Now, where's the audio frequency range?
20 to 20K.
20 to 20K, right? This amplifier has been dying for 2 decades already before we even enter the audio frequency range. So what do we build amplifiers to work with? We build op amps as far as have infinite gain in the region we're operating them. These poor amplifiers that we build don't have this high gain. What's important is the gain in this region here. It's horrible. It's dropped way down from what we had for our DC gain. And furthermore, it changes with frequency. Is that good? Not at all. The only saving grace is that it's still high enough here that we still get pretty good feedback performance. It's way below what we had at DC, but it's still high enough that we get pretty good performance. So can we build circuits that will drive this with, first of all, let's drive it with V out. With minus V out. Well, it's easy to do that. All I need is an amplifier with a gain of -1. I sample the output voltage and drive the counterpart circuit. Is that a good solution? Yeah, it'll work. But what's wrong with this solution? We're trying to build an op amp, right? So you give me 2 good op amps, and I can build a good op amp. So we got a chicken and egg situation, don't we? Okay, so maybe this isn't a good solution. The Verni amplifier may be difficult to build. What about this circuit? We build differential structures all the time. How does this voltage here relate to this voltage here? And opposite in sign. So this voltage here is already what? Minus V out. So what about just taking that and let it drive the counterpart circuit? Okay? Is there any overhead for doing that? Nope, we just connect it a different way. What?
We just need a voltage divider with that.
So now if you put a voltage divider in, that might not be too hard to build if you want to make that so that the pole doesn't move away in the right half plane. So here's what happens now as a function of that feedback factor. As you change this GMP from 0 to some positive value, the gain increases and it stays negative. And then when that pole crosses the origin, it jumps up to a high positive gain and comes back down like this. And it becomes infinite, as we saw at some values. Okay. So if we stop right here, we have an infinite gain function. So, but we had the problem, we said, that the op amp becomes unstable. Oh, back to the old concern that I avoided using that term for 3 lectures now. It hurts me so much I won't even say it, but you can see it written there. So we've got a problem. And I think that the concerns about this poison that I just described is one reason people are afraid to really look at these kind of structures. Oh, it can be shown that the feedback amplifier is usually stable even if the open loop op amp is unstable. That changed the game a little bit, doesn't it? Because we don't use the op amp open loop. In fact, we're going to show after pizza that the feedback performance can actually be enhanced if the open loop amplifier is unstable.
Yeah, that's time.
Is it time?
Yeah.
Okay, let's take a break.